November 5th, 2025. Lowell Observatory, Arizona. The screen flickers to life in the darkened control room. Chi-Chung Jong leans forward, his breath catching. The Discovery telescope has just captured something that shouldn't exist. A compact sphere of light hangs suspended in the cosmic void, where Comet 3I Atlas should be displaying a magnificent tail, the natural consequence of a close solar encounter. But there is no tail, no spray of debris, just a tight, focused sphere that seems to defy everything we know about comets. He reaches for his phone. The image uploads to social media within seconds. Within hours, it will ignite a firestorm of speculation that reaches the highest levels of NASA. Because this isn't just any comet. This is an interstellar visitor, and it's behaving like nothing we've ever seen before. 6 months earlier, a different story was unfolding in the Chilean night. July 1st, 2025. The Atlas telescope in Rio Hurtado, part of NASA's Planetary Defense Network, was methodically scanning the sky. Its mission: to detect asteroids that might threaten Earth. What it found instead would challenge our understanding of what travels between the stars. Larry Denau spotted it first. A faint smudge of light, magnitude 18, barely visible even to the powerful survey telescope. Moving. Fast. Impossibly fast for anything bound to our sun's gravity. The object was tearing through space at 140,000 miles per hour. A velocity that spoke of distant origins and a trajectory that would never return. The Discovery observation went to the Minor Planet Center with a temporary designation. Within days, orbital calculations confirmed what the team already suspected. This wasn't from here. The object's path traced back beyond our solar system, beyond the Oort cloud, into the vast empty spaces between stars. It was given a name that would soon become the subject of intense global scrutiny. 3I Atlas. The third interstellar object ever detected by humanity. But here's what makes your spine tingle with unease. We should have seen it coming months before we did. NASA's Transiting Exoplanet Survey satellite had been staring at that exact patch of sky in May, capturing frame after frame. When scientists went back through the archives, there it was. 3I Atlas, already bright, already active, 6.4 astronomical units from the sun. This was a distance where comets should be dormant, frozen solid, showing no signs of life whatsoever. It was already outgassing, already spewing material into space, and nobody had noticed. Dr. Emily Saunders, a planetary scientist at NASA, would later call it a monument of a discovery. But in those first weeks, it was chaos. Observatories around the world swung their telescopes toward the visitor. The Hubble Space Telescope captured its first images on July 21st. What it revealed sent ripples through the astronomical community. The object had a nucleus somewhere between 440 meters and 5.6 kilometers across, a massive uncertainty range that spoke to how difficult this thing was to observe. It was wrapped in a teardrop-shaped cocoon of gas and dust, a coma that stretched an incredible 26,000 kilometers across, nearly twice the diameter of Earth. For something supposedly so far from the sun, it was shockingly active. The James Webb Space Telescope turned its infrared eye toward the object in August. What it found was even stranger. The coma was filled with carbon dioxide, not water vapor, which dominates most comets. Carbon dioxide. This meant the object had formed somewhere unimaginably cold, far from any star's warmth. It carried with it a chemical signature of deep space, of regions so remote and frigid that even hydrogen would freeze solid. But it was the spectroscopic observations from the Keck Observatory in Hawaii that raised the first real red flags. The data came back on August 24th, and the researchers had to run it multiple times to confirm what they were seeing. Nickel. The comet was emitting nickel gas, and no iron. Harvard astrophysicist Avi Loeb was among the first to point out the significance. In all the comets ever observed, from our solar system or beyond, none had shown nickel emissions without iron. The only place this chemical signature appeared naturally was in industrial nickel alloys created by human metallurgy. The emission radius was enormous, 600 kilometers for nickel, 840 for cyanide. This wasn't trace contamination. This was substantial, puzzling, and completely unprecedented. The object should have been predictable. Comets are ancient, but their behavior follows well-understood physics. As they approach the sun, frozen ices sublimate, creating pressure that jets material outward. This forms the iconic tail, always pointing away from the solar wind. Always. It's one of the most fundamental rules of cometary behavior. 3I Atlas was breaking that rule. In July and August, observations revealed something that made no geometric sense. The object was displaying a sunward jet, an anti-tail. Material was being ejected toward the sun, not away from it. This wasn't an optical illusion caused by viewing angle, the kind of perspective trick that sometimes makes comet tails appear to point in odd directions. This was real, physical matter traveling in the wrong direction. Loeb and his team published a paper noting the anomaly. Most astronomers tried to explain it away. Irregular nucleus rotation, asymmetric heating, localized outgassing from a particularly volatile patch. But the explanations felt strained, forced to fit observations that didn't want to cooperate. Then there was the trajectory itself. When researchers calculated the object's path through the galaxy, they found something with a probability of just 0.2%. The comet's retrograde orbit was aligned to within 5 degrees of our solar system's ecliptic plane, the plane where all the planets orbit, as if it had intentionally threaded the needle between worlds. Someone ran the numbers on where it came from. The trajectory, extrapolated backward through space and time, pointed to a specific region of sky, a patch of space 9 degrees from the direction of the famous WOW signal, detected in 1977, the most compelling candidate for an extraterrestrial radio transmission ever recorded. The probability of this alignment occurring by chance, 0.6%. Coincidence piles upon coincidence, each one individually explainable. Together, they form a pattern that's harder to dismiss. October 29th, 2025. Perihelion. This was the moment of truth. As 3I Atlas reached its closest point to the sun, 1.4 astronomical units, every available sensor in the solar system was watching. The Perseverance and Curiosity rovers on Mars, the Mars Reconnaissance Orbiter, the European Space Agency's Mars Express and Trace Gas Orbiter, the Parker Solar Probe, designed to study the sun's corona, the newly launched Europa Clipper, bound for Jupiter's frozen moon, even the Punch mission, 4 spacecraft arrayed along Earth's terminator, watching the solar wind. For a comet, perihelion is the most violent and spectacular phase. The heat from the sun should cause massive outbursts. Dust and gas should explode outward. The object should brighten dramatically, become more active. Potential even fragment under the thermal stress. This is when comets reveal their true nature. 3. I/ATLAS brightened, but not in the way comets are supposed to brighten. It became 5 times brighter in the green spectral band almost overnight. This was faster than any known comet at similar distances. Faster than Oort cloud, Comets. Faster than Jupiter family comets. Faster than anything in the astronomical record. And it turned blue, bluer than the sun itself. NASA's Jet Propulsion Laboratory released orbital data on October 29th that stopped conversations mid-sentence. The object was exhibiting non-gravitational acceleration. Its trajectory was changing in ways that couldn't be explained by the sun's gravity alone. The numbers were specific and troubling. A radial acceleration away from the sun of 135 kilometers per day squared, and a transverse acceleration of 60 kilometers per day squared. Now, non-gravitational acceleration isn't proof of anything artificial. Comets experience it all the time through outgassing. As volatile ices vaporize, they create jets that push the nucleus in various directions. It's natural. It's expected. But the magnitude matters. Loeb calculated the implications. If this acceleration was caused by natural outgassing, 3I/ATL AS would have needed to lose more than 13% of its total mass during perihelion. 13% in one close pass. That's not impossible. Some comets have done it. But when they do, they create massive dust clouds that last for months. They develop tails spanning millions of kilometers. They outshine nearby stars. You can't lose 13% of your mass quietly. November 5th. Post-perihelion observations resume. This is where everything crystallizes into something genuinely disturbing. Qicheng Zhang's images from the Discovery telescope show a compact light source. No clear tail. The coma hasn't expanded into the massive cloud that 13% mass loss would require. Other observatories confirm it. The Virtual Telescope project in Italy captures the same thing. A tight, focused sphere of light. For comparison, Zhang photographs Comet Lemon from our solar system on November 3rd. There it is. A clear, beautiful cometary tail streaming away from the sun, exactly as physics predicts. This is what comets look like after perihelion. This is normal. 3I/ATLAS looks nothing like that. The Minor Planet Center releases updated orbital data. The non-gravitational acceleration is still there, now measured at 3.7 standard deviations above zero. That's statistically significant. That's real. But it's been reduced by a third, compared to perihelion values. The object is accelerating, but the expected massive gas cloud isn't materializing. NASA's Swift Observatory had measured water loss earlier. 40 kilograms per second, like a fire hose running at full blast. This was happening 3 astronomical units from the sun, far beyond where water should sublimate. At least 8% of the surface had to be active to produce that much water vapor. Most comets have 3 to 5% active surface area. Everything about this object is turned up to 11. It's brighter, more active, faster, stranger than any comet should be. And yet it's not producing the debris field that this level of activity demands. Let's talk about the elephant in the room, the question everyone's asking, but few scientists want to voice publicly. Could it be artificial? Dr. Avi Loeb, former chair of Harvard's astronomy department, has been the most prominent voice suggesting we shouldn't dismiss the possibility. His argument isn't based on wild speculation. It's based on accumulating anomalies. On his self-created Loeb scale for rating the likelihood of extraterrestrial technology, he rates 3I/ATLAS as a 4 out of 10. Not certain. Not even probable. But anomalous enough to warrant serious consideration. 20 scientists signed a paper in September exploring the possibility. Not claiming it as fact. Not building bunkers for the alien invasion. Simply noting that the object displays characteristics we might expect from an artificial probe, using a natural body as camouflage. Humanity has done this. We've sent probes on interstellar trajectories. Pioneer 10 and 11. Voyager 1 and 2. They're traveling through the galaxy right now, indistinguishable from space debris to any distant observer. If we can do it, why couldn't someone else? The counter-arguments are strong. SETI scanned 3, I/ATLAS for radio emissions. Nothing. No regular pulses. No structured signals. No communication attempts. The object's composition, while unusual, can be explained by formation in an exotic stellar environment. The nickel emissions, while unprecedented, might just represent chemistry we haven't encountered before. NASA released a statement on September 11th firmly rejecting the spacecraft hypothesis. The official position. This is a natural comet exhibiting unusual but explainable behavior. Most mainstream astronomers agree. The speculation, they say, distracts from the real science of studying a genuine interstellar visitor. But the debate reflects something deeper. A tension between caution and curiosity, between the desire to understand and the fear of looking foolish. Congressman Carlos Luna wrote to NASA Administrator Sean Duffy in early November. His letter requested full disclosure of all data on 3 I/ATLAS. The information, he wrote, is of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system. The request reflects public pressure. Social media has been ablaze with speculation. Alleged leaked images purporting to show a cylindrical structure above Mars went viral, despite NASA explaining it was a known imaging artifact. The Perseverance rover's navcam captured 3 I/ATLAS from 38 million kilometers away, and the image shows a bright, elongated shape. Online forums exploded with claims of obvious artificial structures. The problem with viral speculation is that it obscures genuine mystery. Yes, the leaked image claims are almost certainly false. Yes, most of the wild theories are baseless. But underneath the noise, there are real, documented anomalies that deserve investigation without stigma. The European Space Agency's Trace Gas Orbiter photographed the object from Mars orbit in early October. It captured a bright coma, but no tail. ESA explained that the tail was too dim to photograph against the background stars. That's a reasonable explanation. But it's also another data point in a pattern of missing tails, absent debris, and behavior that doesn't quite fit. Here's what makes 3 I/ATLAS fundamentally important, regardless of whether it's natural or artificial. It's teaching us about what exists between the stars. For billions of years, objects have been traveling through the galaxy, following trajectories shaped by stellar motions, galactic tides, and close encounters with other systems. They carry with them the chemical signatures of their birthplaces. They are time capsules from regions we can never directly visit. Before 2017, we had never detected an interstellar object. Never. Astronomers had predicted they must exist. The math showed that solar systems must occasionally eject material that escapes into the galaxy. But finding one requires being in the right place at the right time, with telescopes sensitive enough to spot something moving fast against the cosmic background. Then came Oumuamua, the first. Its bizarre elongated shape and non-gravitational acceleration sparked immediate controversy. Was it a comet without visible outgassing? An asteroid with unusual properties? Or something else entirely? We didn't get enough data before it left. The mystery remains unsolved. 2 years later, 2I/Borisov arrived. This one was easy. It looked like a comet, acted like a comet, had the chemical composition of a comet. It was reassuring in its normalcy, proof that most interstellar visitors would be recognizable, understandable objects. 3I/ATLAS is neither reassuring nor easily categorized. It has cometary features, but violates cometary behavior. It has an icy composition, but exhibits industrial chemistry. It brightens like an active comet, but lacks the expected debris field. If this comet originated in the thick disk of the Milky Way, as some orbital analyses suggest, it could be 7 billion years old. Older than our Sun. Older than Earth. It would have formed when the galaxy was younger, when star formation rates were higher, when the universe itself looked different. What was space like 7 billion years ago? What kinds of stellar nurseries existed? What exotic ices could condense in those environments? We don't know. Every interstellar object is a messenger from conditions we can only guess at. The object is leaving now. Its trajectory takes it past Jupiter in early December, giving NASA's Juno spacecraft and ESA's JUICE probe brief windows to observe. Then it's gone, accelerating back into the darkness between stars. We'll never see it again. It will spend millions of years traveling through the galaxy until, perhaps, it encounters another solar system, where other beings might look up and wonder. But the questions remain. The data is being analyzed. Papers are being written. Debates are raging in conference rooms and comment sections. The scientific process grinds forward, sorting truth from speculation, signal from noise. James Webb is scheduled to observe 3I/ATLAS again in December, after perihelion heat has finished its work. The spectroscopic data will reveal the composition of material ejected from deep within the nucleus. Not just surface chemistry, but interior composition. What's inside this thing? What is it really made of? Hubble will conduct ultraviolet spectroscopy in November, measuring sulfur to oxygen ratios and gas emission composition as the comet retreats. These observations will continue for months, tracking how the object evolves as it returns to the cold of deep space. The Vera Rubin Observatory is coming online soon. Its wide-field survey will detect between 6 and 50 interstellar objects per decade. We're about to enter an era where these visitors become routine rather than exceptional. We'll build statistical samples. We'll categorize. We'll understand the diversity of what travels between worlds. And maybe, in that flood of new data, we'll find something that makes 3I/ATLAS look conventional. Or maybe we'll find something even stranger. Something that forces us to completely rethink what's possible. Let's return to that November 5th image. That compact sphere of light, where a tail should be. There are 2 ways to interpret what we're seeing. The conventional interpretation. 3I/ATLAS is a chemically unusual comet, perhaps a fragment from a disrupted exoplanet, ejected into space during a catastrophic collision. Its unusual composition produces outgassing behavior we haven't encountered before. The nickel emissions come from previously unknown mineral formations. The anti-tail is caused by complex rotational dynamics. The missing debris is there, but too diffuse to photograph. The trajectory alignment is coincidence. The non-gravitational acceleration is standard cometary behavior. We just need more data to fit all the pieces together. This interpretation is probably correct. Most astronomers believe it. The scientific consensus, built on centuries of observational astronomy and cometary physics, supports it. But there's another interpretation that's harder to dismiss than it should be. What if some interstellar probes do travel hidden inside natural bodies? What if you wanted to survey other solar systems, and you knew that manufactured spacecraft would be obvious, detectable, alarming to any inhabitants? You might choose to hollow out an asteroid or comet, install your instruments inside natural rock and ice, and let orbital mechanics do the rest. Your probe would look natural, move naturally, be ignored until the moment you chose to act. The emissions could be waste heat from internal systems. The acceleration could be small course corrections. The missing tail could be mass ejected more carefully than cometary sublimation allows. The nickel signature could be industrial in the most literal sense. We have no evidence for this. None. It's speculation bordering on science fiction, but it's not physically impossible. And that makes it a hypothesis worth examining, even if only to definitively rule it out. Science works by eliminating possibilities. You observe. You hypothesize. You test. You discard what doesn't fit the data. You remain open to surprises while maintaining rigorous standards of evidence. The danger isn't considering unusual hypotheses. The danger is closing off inquiry because the implications feel too strange. For centuries, scientists dismissed reports of meteorites because rocks couldn't fall from the sky. Continental drift was ridiculed for decades before becoming accepted geology. Quantum mechanics violated every intuition about reality, but turned out to be true. We live in a universe with 400 billion stars in our galaxy alone, 2 trillion galaxies in the observable universe. The numbers are so vast that even wildly improbable things become statistically likely. If technological civilizations arise anywhere, ever, with any frequency at all, then the galaxy should contain artifacts of their existence. The Fermi paradox asks why we haven't seen them. Maybe we're alone. Maybe intelligence is vanishingly rare. Maybe civilizations destroy themselves before spreading. Or maybe we're not looking properly. Maybe we're expecting radio signals and gleaming spacecraft when the reality is more subtle, more integrated with natural processes. 3I/ATLAS probably isn't artificial. The odds are strongly against it. But the only way to be sure is to investigate thoroughly, without prejudice, following evidence wherever it leads. December 2025. The final observations. Webb's infrared spectrograph captures the last detailed data as the object recedes toward Jupiter. The spectroscopic signature reveals complex hydrocarbons, carbon monoxide, ammonia, methane. The chemistry of deep space and ancient ice. Material unchanged for billions of years, now briefly warmed by our sun before returning to the cosmic freeze. The data shows no geometric structures, no right angles, no obvious manufactured components. The object behaves like a comet in all fundamental ways, however unusual its specific characteristics might be. The scientific papers start appearing in journals. Peer review dissects every claim. The anti-tail is explained by unusual dust grain properties combined with solar radiation pressure. The nickel emissions are attributed to a mineral composition rich in sulfides, possible in metal-rich stellar environments. The trajectory alignment is acknowledged as unusual, but not beyond the range of natural occurrence. The case closes. 3I/ATLAS is classified as a natural interstellar comet with exotic but explicable properties. The speculation fades. Public attention moves to the next mystery. But some questions linger in the minds of researchers who watched it most carefully. Why did it brighten so fast? Why is there so little debris? What produced that sustained non-gravitational acceleration without obvious outgassing? Why does its surface activity pattern differ so dramatically from every other comet ever studied? These aren't questions that suggest artificial origins. They're questions that suggest our understanding of cometary physics, based entirely on objects from our own solar system, might be incomplete. That the galaxy produces comets in ways we haven't imagined. That chemistry and conditions in other stellar neighborhoods create objects genuinely unlike anything in our local environment. That's the real value of 3I/ATLAS. Not as evidence for aliens, but as proof of how limited our perspective has been. 7 billion years ago, in a star system we'll never identify, in a region of the galaxy we can't observe directly, a planet was forming. Or perhaps being destroyed. Material was cast into space. A fragment of ice and rock, somewhere between 0.5 kilometer and 6 kilometers across, found itself on an escape trajectory. It traveled. For billions of years it traveled, through the emptiness between stars, through regions where the nearest sun is a dim point of light, through voids where nothing exists for light years in any direction. It was bathed in cosmic rays, bombarded by interstellar dust, slowly altered by radiation, and the occasional molecule of gas drifting in the galactic medium. It watched supernovae explode in the distance, passed through nebulae where new stars were being born, witnessed the slow evolution of the galaxy's spiral arms. All of this in silence, in darkness, in cold that would freeze even helium solid. Until July 2025, when its random trajectory happened to intersect with a yellow dwarf star at the edge of one spiral arm. A star with 8 planets, several moons, and one planet where a technological species had evolved. Where beings had built telescopes and satellites and rovers. Where someone was watching the night sky when a faint smudge of light appeared moving faster than anything should move. We got to see it. For a few months, we got to observe a visitor from beyond. To measure its chemistry, track its motion, argue about its nature. To be reminded that the universe is larger and stranger than we can easily comprehend. The comet will leave our solar system in early 2026. It will pass beyond Jupiter, beyond Saturn, beyond Neptune and Pluto. It will cross the Kuiper Belt, return to the Oort cloud's outer reaches, and then keep going. In 10,000 years, it will be light years away. In 1,000,000 years, it will encounter other stars, perhaps with their own curious inhabitants watching an unexpected visitor appear in their skies. We built something to last. Voyager 1 and 2 carry golden records with sounds and images from Earth. Messages for anyone who might find them. They include music, greetings in dozens of languages, diagrams of our location in the galaxy. They're moving at 40,000 miles per hour, which feels fast until you realize it will take 40,000 years to reach another star. If intelligent beings exist elsewhere, if they're exploring as we are, then the galaxy might be crisscrossed with probes and artifacts, messages and machines, all traveling on trajectories that last longer than empires. We might share the cosmos with countless others, separated not by impossible distances, but by impossible time scales. Ships passing in the billion-year night. Or maybe we're alone. Maybe intelligence is so rare that we're the only ones looking up, the only ones wondering, the only ones trying to understand. Either answer is humbling. Either answer should fill us with a mixture of wonder and responsibility. We're conscious matter. We're the universe trying to understand itself. And whether we're the only example or one of billions, that's extraordinary. November 8th, 2025. You're reading this now. Somewhere above you, 3I/ATLAS is accelerating away from Earth. You can't see it without a telescope. It's already fading, returning to the darkness it emerged from. In a few weeks, it will be beyond our observational reach. The story will be over. Except it won't be. The data will be analyzed for years. New insights will emerge. Theories will be refined. We'll understand more about how comets form in other systems, how they survive journeys measured in billions of years, how they interact with stars they've never encountered before. And somewhere, someone is building better telescopes, bigger surveys, more sensitive instruments. The Vera Rubin Observatory will see first light. The next generation of space telescopes will launch. We'll develop new techniques for studying transient objects moving through the solar system. We'll find more interstellar visitors. Most will be boring. Some will be interesting. One or two might be genuinely revolutionary. This is how science advances. Not through sudden revelations, but through the patient accumulation of observations. Through the slow refinement of theories. Through the willingness to be surprised by what we find. 3. I/ATLAS didn't provide easy answers. It raised questions that will take decades to fully resolve. But that's good. That's how it should be. The universe doesn't owe us explanations that fit our current understanding. It simply is what it is. And our job is to figure it out. The night sky looks the same as it did before July 2025. The stars occupy their familiar positions. The planets follow their ordained paths. Nothing has changed, except everything has changed. Because now we know, with certainty, that things travel between those stars, that the galaxy is connected by silent travelers moving through the void, that what seems empty is actually crossed by countless objects following trajectories written billions of years ago. And sometimes, just sometimes, one of them passes close enough for us to see it, to study it, to wonder at it. That makes every clear night a little more magical, makes every telescope a little more important, makes every patient astronomer who spends cold nights staring at CCD screens a little more heroic. They're watching, waiting, recording, building our map of what's out there. And when the next one comes, whenever that might be, we'll be ready. With better instruments, better techniques, better questions. Because that's what we do. We're the species that looks up and asks why. That builds machines to extend our senses beyond human limits. That refuses to accept mystery as an endpoint when it can be a beginning. 3. I/ATLAS came from 7 billion years in the past. From a star we'll never know. From conditions we can only guess at. It brought with it chemistry that doesn't exist in our solar system. Behavior that doesn't match our models. Questions that don't have easy answers. And then it left, carrying its secrets back into the darkness. Maybe it was just a comet. Strange, yes. Unusual, certainly. But ultimately natural. Explicable. Another piece of the vast puzzle of how the galaxy works. Or maybe, just maybe, it was something more. Something that watched us as we watched it. something that recorded our radio emissions, our spacecraft, our attempts to understand what we were seeing. Something that will carry information about this small blue world back to whatever created it, if anything did. We may never know. The comet is leaving. The window is closing. The moment is passing. But we were here. We saw it. We measured it. We wondered at it. And that has to be enough. Because in a universe as vast and ancient as ours, being present for even a single moment of mystery is a gift beyond calculation. Being able to observe, to question, to seek understanding even when answers elude us, that's the privilege of consciousness itself. 3i Atlas is gone now, but it changed something. Maybe just in how we think about interstellar space. Maybe in how we approach anomalous observations. Maybe in reminding us that the universe still has the power to surprise us, to challenge us, to make us question assumptions we didn't even know we were making. And in the end, isn't that what we're really looking for? Not answers that close doors, but questions that open them. Not certainty that ends inquiry, but mystery that fuels it. The comet brought us mystery. It brought us wonder. It brought us the discomfort of not quite understanding what we were seeing. And for that, we should be grateful. Because the day the universe stops surprising us is the day we stop being truly alive. Look up tonight. The stars are waiting, and somewhere among them, a visitor from impossible distance is continuing its journey, carrying with it the memory of our brief encounter. We watched it pass. We measured its light. We wondered at its strangeness,